So it's my pleasure to present our next speaker, David Bang, from the University of Warwick, who's going to speak about asymptotic shape of the concave majorant of a Lévy process. Please, David.
Thank you. Yeah, so this talk will be based on a paper that's with Jorge Gonzalez and Alexander Miatrovic, my supervisor and collaborator. So there's going to be three aspects of this talk. So what is a concave majorant? What kind of shape statistics are we interested in when considering a concave majorant? What are we interested in describing? And can we say anything about dependence and limit theorems when we construct stuff like this? Right. So say we consider a sample path of a Lévy process X on 0t. So we have it starts at 0 almost surely. It's a cat-like process. It's a continuous time stochastic process. Has some big jumps, as we can see here, and has possibly infinitely many small jumps. This is just a completely general Lévy path. So what is it then that we are really interested in understanding about such a process? So the other way. So this is a concave majorant. Okay, so what is a concave majorant? This is the smallest concave function that bounds the path piecewise from above. Okay. So for all times, Ct frown of t will be larger than or equal to the path at time t. Right? So you can sort of think about it as if you take a blanket and drop out over the Lévy process, right? It can't dip between 2 points, of course, so it's end up being piecewise linear. As you can see, you have these pieces of linearity here, here, and so on. Right? There's going to be infinitely many of these pieces of linearity, possibly. And these pieces of linearity we'll call phases. Right? They'll have a horizontal length and a height. Right? So this is the object we're really interested in trying to describe. Okay. So what are the kind of as the shape statistics we're really interested in trying to describe when we look at asymptotic behavior? Well, first of all, as the new picture suggests, is that we're interested in the maximum. So the supremum, Ct frown bar, and we're interested in time at which the supremum is attained. Okay, so these are two of the things we're interested in. We're interested in describing how the endpoint behaves, and we're interested in describing how the length of the concave majorant. Right. So what we're really interested in is constructing limit theorems for the joint law of these things, for the joint quadruplet of all of these objects. Right. The length, the supremum, time supremum, and the endpoint. And then we're interested in describing specifically the asymptotic mean of the length and describing the limit fluctuations around the asymptotic mean. And surprisingly, well, we can say something about the limit dependence between these objects. Specifically, how does these relate to each other when we take a limit going to infinity? So this is really the main idea and the main object behind this talk, trying to describe really this object. And it's become increasingly popular to describe specifically concave majorant, convex majorants of random walks, and not much has been known about Lévy processes. Right? So that's also why we have created this paper discussing what things look like in this case, at least for the length, but in general other geometric properties of convex hulls is of interest to describe. Right. So can we say anything about roughly of what size the asymptotic mean is of the length of the concave majorant? Well, if we denote epsilon t frown to be the length of the convex hull, sorry, the concave majorant, and we consider a very trivial upper bound, you take the length t, and then you add the first, so the supremum, you actually add 2 times the supremum, and then you add the endpoint, right? So you get this box, put this box over the concave majorant. Yeah. This is an upper bound. Then it's clear that this is an upper bound, and you divide by t. clearly a trivial lower bound is that we say that, well, okay, the lower bound is just the straight line from 0 to t. Right? This is a lower bound. So if we have 0 mean and slightly more than first moment, so 1 first epsilon moment, it turns out that this thing, the upper bound, specifically converges to 1, almost surely. So we can see that we need at least the leading term of the asymptotic mean needs to be around t. So what are the main goals from the talk from here on out? So we're going to describe the limit fluctuation of the asymptotic length of the concave majorant around its asymptotic mean, trying to really clearly describe what this object is. And then we're going to construct distributional limit theorems, right, for the different center statistics and consider limit dependence. And we're going to do this for different regimes. So for second moment and then for domain of attraction. So the first main theorem for second moment is going to be constructed like this. So say we have a Lévy process with the Lévy measure nu. We assume that it has 0 mean. It has positive finite second moment, and we describe that by sigma, which that's the square root of the variance. And for all t, we describe this deterministic function theta t, which is the 1/2 the integral of x squared, the positive part of log, over the minimum between t and x squared, integrated with respect to nu. Okay, so this comes up in the centering of the length. So let's see the big limit theorem. Okay, then as t goes to infinity, we have a quadruplet that converges jointly in distribution to this quadruplet. Okay? So what are the different aspects of this? Well, the first entrance here is going to be the length centered around t, as we saw before. This is the sort of the natural thing. We're going to have some ht, some stochastic thing in this case, and theta t. Okay, so what is ht? So ht is going to be the number of maximal faces that has horizontal length larger than 1. Okay, so what does that mumbo jumbo mean? So if we consider such a picture, right? So as we've discussed, a face has a horizontal length and a height. Right? So we say that a face like this is maximal if it contains all the faces of the same slope, right? So faces that has the same slope are going to come back to back because they are ordered in decreasing slope, right? And if we put faces of the same slope into one slope, this is the maximal faces. So what we do is that we count up all the maximal faces that has horizontal length, so the length this way, that's larger than 1. Okay. This is our h. This is a stochastic thing. But this turns out to really describe well the centering of this, of the length, right? So we subtract ht, the number of maximal faces of larger size or of moderate size, and then we add theta t, so the deterministic function we had from before, right? The scaling is going to be square root log t. So this is the size of the fluctuations in the limit. Yeah. What do we more know? Well, this is a sort of CLT type result, right? However, we also have a CLT for the maximal faces itself, right? So that has the centering log t, and again scaling square root log t. Okay. We now consider the large triplet here, and those are the shape statistics we were also interested in. We have the maximum divided by square root t, the endpoint divided by square root t again, and then we have the time of the supremum, which has scaling t. So what does this mean? So in the limit, we're going to have, say we have a b is the standard Brownian motion, we have b bar is the supremum, and rho is the unique time at which you attain your supremum. Yeah. So we have also two standard random variables, Z1 and Z2, that are independent, and they're independent of b. Right. So all three of these are independent of each other. Yeah. What happens? Well, in the limit, this converges jointly. But anything that has to do with these three shape statistics, right? So the supremum, endpoint, and the time of the supremum, in the limit, they're independent of what had to do with the length, right? What the the length and the number of maximal phases. Right? So we have limit independence in this case, which is very surprising that we get this very funny structure that we have independence in the limit. And it might seem unintuitive why this is the case, but it turns out that for epsilon t frown and ht, none of the small phases are going to contribute to the limit fluctuations. Okay? It's only going to be the moderate sized phases that contribute in aggregate. Okay? That contribute to the limit fluctuations. And very differently for these guys here, it's only going to be the largest few phases that actually contribute to the limit. And this is the main reason behind why we could prove something like a limit independence between these objects. So one could say, okay, and that's fine, but we have a stochastic centering in this case, right? But what's good is that we have the CLT here as well. So a nice corollary of the main theorem is that we can actually have a CLT with a deterministic centering. So if we take the length, subtract t, subtract square root, so subtract log t, multiply by sigma squared over 2, and add the deterministic function theta, then scaling by square root log t gives us a standard random variable set, multiplied by sigma squared, square root 3 over 2. So the only thing here is that we are penalized by having a slightly larger variance now, because we no longer have a very nicely fitted stochastic centering, but we have a deterministic centering. And in this case, theta t is going to be little o of log t. Okay. So a second part of this corollary could be that we can even, under slightly sharper assumptions, get rid of this theta t in the centering. So if we assume that x squared log plus of norm of x, square root of that, nu dx, if this is a finite integral, then it turns out that theta t is going to be little of square root log t instead. Yeah. So as we can see from the scaling, this term will eat up theta t. Yeah. So instead, we'll have a very simple, nice CLT where you really have a very simple centering, just t minus square root, so t minus log t. And again, we have the same limit as before, a constant times the standard normal random variable. So what happens if we want to go outside of second moment? Well, the next natural step would be to consider domain of attraction. So can we say anything about processes that are in the domain of attraction? Well, if you consider a Lévy process x in the domain of attraction of an alpha stable law for some alpha between 0 and 2 corresponding to the Gaussian limit, what does that mean? What do we mean when we say this? Well, we assume that there exists a function, positive function at, and an alpha stable Lévy process S alpha, such that xt scaled by at converges in distribution to S alpha at time 1 as t goes to infinity. So in this case, at is going to be regular varying, so it has the form t to 1 over alpha times L of t, where L of t is a slowly varying function. So this is one of the key points. So what is another very important thing that pops up in actually, as soon as you consider domain of attraction, some very funny object pops up in the limit. So these are it's a stick breaking process. I don't know if you've heard about it before, but you will definitely hear about it later again. So this is a uniform stick breaking process on 0, 1. So with stick remainders capital Ln, and it's given by an IID uniform sequence Vn. So what does that mean? Well, you take a stick of length 1, you take a uniform random variable on this interval, and you break off a part. This is the part you break off. You break small curly L1 off, right? And then you're left with this part. And then you take a new random variable, L2, and then you break the next part off, and so on, right? So all of these are your sticks. Yeah. And then the stick remainders are what's left, right? Because that's the length from 0 up to L1. That was what was left after breaking off stick 1. And this turns out to be very crucial to understand the limiting behavior in the domain of attraction cases. So consider a process in the domain of attraction with alpha stable law, alpha now between 1 and 2. So the behavior is very different if you consider heavy tail. So alpha, no, sorry, alpha between 0 and 1 instead. Right. So now you can see the scaling change. The scaling changed to this function here. So at squared over t. The centering also got significantly more simple. It's just t now. And we have the scalings at and t. So what we have now is this limit theorem that says that in distribution, this converges as t goes to infinity to this quadruplet. Okay. So let's take them each at a time. So here, as you see, everything depends on S alpha and Ln. So we can't hope for any independence in the limit here. This is very dependent, right? However, these have very nice interpretations. So the last entrance here will be the time at which Sn attains its supremum. This will be the endpoint of the stable process, and this will be the supremum of the stable process. In this case, Ln is the uniform stick breaking process. S alpha n is a sequence of independent copies of S alpha time 1, and these are independent. So these are the three that have very nice interpretations. Unfortunately, the limit for the length centered has not the same nice interpretation. This is slightly more on a difficult form. However, it is possible to show the tail behavior of this guy. So it is possible to show this as the same tail behavior as the stable process squared. So this has so it has a very nice tail behavior, but as nice an interpretation as this triplet we can't unfortunately get. Right. So in this case, it's of course for zero mean, and this right. Okay. Go back, backtracking. So why isn't this an infinite sum and depending on the stick breaking process? So the reason is that all phases are going to contribute to the limit fluctuation in this case. Right? So we see these LNs sort of represent that we have sum infinitely over all of the sticks. And this means that if you look into the proof, really all phases contribute to the limit fluctuation, not only the moderate sized phases, as we saw in the second moment case. And like this. Okay. So now if we instead consider non-zero mean, we can have a similar, well, not similar, but there exist results as well, right? In this case, it's very important to split the behavior between a positive mean and negative mean, especially because we're considering concave majorant, right? So this really describes how this is going to behave. In the case of positive mean, we need to change the centerings a bit. So we need to add the constant 1 plus mu squared, square root of that. We need to censor the supremum and the endpoints by mu times t, but the scalings are the same, right? In these two cases, at least, in this case, the scaling is now slightly different. It's just at. Before, the leading term was t to 2 over alpha minus 1, and then the slowly varying function squared. This was the scaling before in the zero mean case, right? And now it's just at, so it would just be t to 1 over alpha times the slowly varying function. And the limit is very nice. Again, we have S alpha times this triplet, so all interests purely depend on S alpha at the endpoint. Right? Now, if it has negative mean, things are very different, and the limit behavior can be described like this, where it now depends on this overall supremum for the entire path. But we don't have time to go into details. So now let's consider the other case. So alpha between 0 and 1. In this case is what we can really show the strongest results. Okay. And so what is this? So we have the quadruplet from before. So length, supremum, endpoint, and time supremum. Everything that depends on the concave majorant. Now let's add all the information from the convex minorant. Yeah. So the length of the convex minorant, this infimum, endpoint, and time of the infimum. Yeah. What turns out is that when alpha is between 0 and 1, we can show joint convergence of the entire thing. Everything that depends on the convex minorant and concave majorant converges jointly to this limit, where the limits depend, as you see here, on the endpoint, the infimum of the endpoint of the stable process and the infimum of the stable process, and here's the supremum. Right. What this means is that we can actually get a result for the convex hull, the entire hull. So we can actually get the entire length of the convex hull, because if you take upsilon t frown plus upsilon small t divided by at, right? This would be the length. This would be the length of the entire convex hull, right? And we just need to scale by at. In that case, we would get in the limit, things would cancel out. We would get 2 of this supremum minus 2 of the infimum. In that case, this thing would 2s alpha over bar minus 2s under bar of 1. So we know exactly the how the length of the entire hull, right? And this is significantly different because in the other cases we only know one at a time. There's a symmetry, so we would know similarly if we only consider the convex majorant, we would know similar results to the other case, but we wouldn't know the joint law of the entire thing. That's only when we're in this case we can produce such a result. The idea behind why this is the case is that we have a very, very narrow or thin majorant and a very tall. So it's easier to come up with bounds that are close to the actual concave majorant. Right, so all of these are quite general results. They're for processes in domain of attraction, right? So they encompass a lot of different results. So you could, for example, subordinated Brownian motion would be, you will be able to apply to these results. Right. So why is it the case? Let's try again. Are the fluctuations very fine, and the scaling of these fluctuations are extremely fine? So you remember this picture from before, and we have the box top as before, and then we have sort of like a hut. So we have 2 different bounds. We have an upper bound and a slightly more non-trivial lower bound, which goes from 0 to the supremum to the endpoint. These are 2 that bound the concave majorant. And in the paper, we also give CLT limit theorems for these 2 objects, for the box top and for the hut. It turns out that the scalings behave very differently, and it shows really where things behave more nicely in the sense that they're very close to each other. So say we consider these 3 settings and we look at the scaling of the Lévy process itself. Of course, if we have alpha equal 2, we need square root t to converge right to a stable distribution. If we are between 1 and 2 and 0 and 1, we know by domain of attraction that we need to scale by at to converge to the stable process. However, how does the scaling differ for the length of the concave majorant, the length of the hut, and the length of the the length of the hut and the length of the box top? Well, for alpha equal 2, there's no scaling is needed for the lower bound, which is very funny. And then square root t, square root of log t, as we saw before, and square root t is needed for the box top. So here we have very different scalings needed for the 3 different objects. In alpha between 1 and 2, it turns out that the scalings between the tent and the concave majorant are the same, whereas we need to slightly differ for the box top. And then for alpha between 0 and 1, they're the same. So this means that when you have a very narrow, very tall case, you can easily bound the object by things that represent it nicely in terms of at least the scaling size. So in that case, it's easier because it's very extreme. There's some very big jumps that control it. So therefore, it's easier to bound and sandwich and show the strong result we had from before. This guy. Right. So proofs. How can we ever hope to prove anything like this? What is the main result? And now I want to advertise a bit for a talk that Jorge is going to do in a few hours. I would definitely recommend you stay around for that because it's very interesting. And it's due to that result that it's even possible to show any of this that I have presented here. So I'll try to go quickly over this so you won't recognize it when you see it later. But the main idea behind this type of theorem is that when you look at the convex, the concave majorant, you can describe it completely in terms of a independent stick breaking process and independent copies of the Lévy process, and look at increments of an independent copy and sticks. Right? So you can completely describe it through purely the process itself, increments of that, and sticks. Right? It's very surprising that you can do this, and this is the reason why we can prove things like this, because we can completely push the problems onto the behavior of sticks and how the stick breaking process behaves. And this is also why we split when we considered the proof before. We split for the size of the phases, because this turns out to be represented by sticks. Right? So there's this really strong connection between the phases and sticks and increments. Okay. And what is this connection? Well, if we look at this quadruplet, which is going to be the length, a slightly different HT, so we call it HT prime. So instead of being the phases of size, horizontal length larger than 1, now we're looking at sticks larger than 1. But you can prove that this approximates really, really well exactly what we're interested in. You have, of course, the length, which is the height squared plus the length squared, and then square root of that. Yeah. And then for the other shape statistics, you have this interpretation. So you have the increments positive only. If you only take the positive parts, of course, you go up to the supremum. And if you only sum the lengths when you go up, you get to the time of the supremum. Right? So you get exactly this triplet, and then we know how to control such an object. Right? We can split such a sum into when, as I described in the beginning, we can split into all small phases and all moderate-sized phases, and show that it's only the moderate size that contribute in aggregate. Right? So this is really the main reason why we can prove anything, and this is the main idea behind the proof. As it says here, this HT prime will be such that this thing is bounded in a 1 as t goes to infinity. Okay, so there's one more thing that was needed to be proven, and that's this theorem, the Gaussian approximation theorem. So if you have a second moment, so this is for the proof of this part is for the proof of the second moment case. This was not needed in the other cases. So you have a second moment, non-zero Lévy measure, and you have some mass at around minus kappa to kappa. We have sigma t, which is sigma squared minus some truncated second moment here. And then we have the Kolmogorov distance between xt divided by square root t and the normal limits, where we just scale. So this is the CDF of standard normal random variable, but we scale by sigma t. And what is already known is that this converges to 0 as t goes to infinity. However, that's not enough. We want to, in the proof, we want to instead of looking at this guy, we want to actually put in a normal distribution and be able to say, okay, this works, right? So we need to know the rate at which this happens, right, in continuous time. This was proven by Kolmogorov for discrete time, but nothing was really shown for the rate in continuous time. So we made a paper that described that happens at this rate. So you can actually show that it's integrable. Kt divided by t from 1 to infinity is actually going to be integrable. And this is also one of the main reasons why we can prove this result. Right, so here are some of the references I talked about. And of course, there's a lot of references on this entire topic, but I didn't want to put all of it here. But yeah, thank you for watching.
Thank you very much. Any questions, please?
So, well, one of the reasons people are interested in convex majorants is because of applications to, mathematical finance, insurance, and all that. So I was wondering if you had any applications in mind for the length of that.
So there is one application that comes to mind where I found doing literature research for this, where they apply it in physics for considering particles and whether they stay inside a light cone. And they use convex hulls to describe the light cone. And then this would be an application for this, where you can describe sort of the length of such light cones and how that behaves over time.
Oh, great. So a second thing is it's really.
Could you speak up a bit, sir?
Sorry. A second thing is that it's really non-trivial, right? To paste together convex minorant and convex majorant, a concave majorant, to get at the convex hull.
Yes, that's very difficult. And sorry, what? Sorry,
yes.
continue.
So I was wondering if now since in this situation you were able to do that complicated study, right? If you had thought about going to higher dimensions and do a pasting together to study maybe length of convex hulls of two-dimensional random walks, which have been the focus of a lot of combinatorial studies recently.
Right. So we haven't thought about going into higher dimension because, first of all, the main ideas behind a lot of these proofs are, well, you know very well, this results on this results here, right? The result of where you use stick breaking process, and this only exists in one dimension. How it's not really known well how you would choose such a description in higher dimensions. And so I would think the only thing that perhaps you would be able to prove would perhaps be in this strong control case. Then maybe you would be able to prove something exactly as you suggest, but I don't know exactly how you would do that. I haven't tried to do it, but it's definitely true that you would need something completely different to prove the other results we have, because they so heavily rely on this very, very nice structure that you get in the one-dimensional case. And also, as you have a very good point, that you can't just because you have this result for the concave majorant, you can't just piece it together with the convex minorant because you don't know the joint law. It's only because we have very strong bounds in this case that we can tell anything. But thank you for the comment.
No more questions? Okay, then let's move